Alright, this video is dedicated to the wild and wacky world of signal detection theory. Signal detection theory is something that comes up a lot in psychology, particularly in psychophysics or the study of sensation and perception, and it's kind of a different way of approaching data, or a different way of approaching analysis or understanding behavior. So we're going to be focusing on what is signal detection theory, why is it so important. I'm going to give you some real life examples, including Where's Waldo, and then I'm going to show you how you can read the results of signal detection theory in the form of ROC curves, or receiver operating characteristic curves. You're going to see those graphs a lot in the literature whenever people use this kind of analysis. Now, before we move on, I want you to pay close attention to a face that's going to walk across the screen, because it's going to be useful in just a moment. Alright, so I hope you got that. We're going to start off by doing some examples of Where's Waldo. So in some of these scenes, Waldo is going to be present, and what I want you to do is keep a track of, do you see him, yes or no. I'm going to give you 5 scenes, and I'm going to give you a couple of seconds to look over each of these scenes. So give it a shot, and keep track of how many of these 5 you see Waldo in. Okay, so how were your results? What you should have been looking for is basically this right here. This little guy right here, Waldo, you should have been looking for him, and if you looked closely, and maybe even if you cheated and paused the video, you probably saw him 3 out of 5 times. And if you wanted to, you could measure your accuracy. You could say that, you know, you got 40% correct, or maybe you got 100% correct if you were right every single time. But is that actually the best way of looking at results? Is just by accuracy? Signal detection theory is going to give us a little bit of a different way of looking at this. This is going to give us a more sensitive approach. And what this basically means is that we can split out, instead of just correct or incorrect about whether Waldo was there, we can actually look at 2 different questions. Was Waldo actually present in the scene, and how did you respond? So let's break these out into yeses and nos. So, was Waldo there? Yes. If he was actually there and you responded yes, then that would be considered a hit. If you responded no, that would be considered a miss. You missed that Waldo was there. But those aren't the only kind of responses. There are 2 more. So if Waldo wasn't actually there, let's say that he was not actually there and you said yes he was, that would be considered a false alarm. If he wasn't actually there and you indeed recognized that he wasn't there, that would be considered a correct rejection. So those are the 4 kinds of ways of responding now. So instead of just correct or incorrect, we have more variety. We have a more sensitive way of looking at our data. So we can turn this into something about psychophysics now. Instead of asking whether or not Waldo was there or not, we can ask whether the stimulus was present and if we perceived that stimulus. And this is going to give us kind of a breakdown of signal versus noise. Okay, so let's explore this idea of signal versus noise. What is the signal? What is the noise? Let's use Waldo again as an example here. Okay, so the signal is going to be Waldo in this case. It's going to be the stimulus that you are attempting to perceive. It's the stimulus that you are listening for, or that you're looking out for. So this right here that the arrow is pointing to, that's our signal. That's what we're looking for. And the noise is going to be everything else in this scene that is not Waldo. So any other color, any other line, anything, even in your environment right now, in your room right now, or wherever it is that you're listening to this, that can be noise. It can be visual, it can be auditory, anything that could potentially distract you from finding Waldo. Okay, but let's say that we wanted to increase our ability to find Waldo. We can do that. If we do that, let's say that we increase Waldo's size, we make him bigger. That's going to be called an increase in sensitivity. In other words, the environment becomes a little bit less noisy in comparison. We've made our stimulus more salient. That signal that we're looking for is now easier to find. But we can also decrease our ability to detect that signal. So if we do that, an example of this would be like if we turn this entire scene in black and white, it's harder to find him now, right? Or if we take out some of the detail, that makes it harder to find Waldo. That's going to be decreasing our sensitivity. So it's decreasing our ability to detect that signal because the environment has now become a little bit noisier. So when we increase sensitivity, what's really going on is that we are increasing our likelihood of getting a correct hit. So whenever he is there and we report that he is there, a hit, or when he's not there and we correctly report that he's not there, a correct rejection. So we're increasing sensitivity like that. But if we were to decrease sensitivity, what that would look like is basically that we're going to have more misses and more false alarms. So we're less likely to see him when he actually is there, and we're more likely to report seeing him when he actually is not there. Now, these differences in sensitivity, they're going to be measured in D prime. And D prime is kind of the dependent variable that you often see in the literature whenever people are using signal detection theory. It's basically a way of measuring the saliency of that stimulus. How salient is it compared to the rest of the noise in the environment? The higher the D prime, the more salient that signal is. Okay. So, let's do one more example. Alright, let's try an auditory example now. So, let's imagine that you're taking a shower and you're listening for your phone to ring. And just like Where's Waldo, I want you to say yes or no, whether or not you heard the stimulus or didn't. This time you're going to be listening out for a ringtone. Okay, so do you hear it? If you said yes, then you're absolutely right. You did hear it. That would be a hit because it was there and you did correctly perceive it to be there. But if you said no, that would be incorrect and that would be considered a miss. It was present, I did play it, but you didn't perceive it. But if you turned up your ringer, that would actually increase the likelihood that you're going to get a hit, right? So it's going to increase our sensitivity, or it's going to increase our D prime for that ringtone. See? You can hear it that time. And because you can hear it that time, that was just an increase in D prime. It now sticks out compared to the noise. In this case, the signal is going to be the ringtone, the noise is going to be the sounds of the shower. So, now listen closely, see if you can hear this one. Okay, if you said that you thought that you heard it, you were actually wrong, you were mistaken. That was a false alarm. You falsely heard something that wasn't actually there. But if you said no, that would be a correct rejection. You didn't hear it because it actually was not present. Okay, so the take-home message to this is don't think about signal detection theory like a theory that can or cannot be proven. Instead, think of it as a new way of approaching data. It's a new way of thinking about how behavior works in the real world. But one of the most difficult things about signal detection theory is trying to find ways to visually represent it. It's not just like using accuracy where you can just use a bar graph. It's much harder than that because now you're using 4 response variables. You're using hits, misses, correct rejections, and false alarms. So if you're reading anything about signal detection theory, you'll probably see a graph like this, and they can be really intimidating because there's usually not a whole lot of instruction about how to interpret what this is trying to convey. But let's break it down. On the y-axis, we have the probability of a hit, and on the x-axis, we have a probability of a false alarm. So on the y-axis, what is the likelihood that the people in this study correctly perceived the stimulus there when it was indeed there, and on the x-axis was likelihood that someone falsely reported perceiving that stimulus when it wasn't actually there. So if we look at the A here, that would be perfect because what we're seeing here is that someone every single time gets a hit and they get no false alarms. If we look at C is going to be chance performance because, because they're just as likely to have a hit as they are a false alarm. But B is probably more what you would see out in the wild, out in the real world, where most of the time they're going to get a hit and correctly reject instead of having a false alarm. So in the case of A, what we have is no misses and no false alarms. In the case of B, we have more hits than false alarms, and in C, we have as many hits as there are false alarms. So the steeper the curve we have here, the higher the D prime. And remember, D prime is what we're looking for because it's kind of the saliency of that stimulus compared to the noise. And we can kind of mathematically represent this by having D prime is equal to kind of the standardized probability of a false alarm subtracted by the standardized probability of a hit. That's a little bit, more difficult than what we're trying to tackle here in this video. I'll post another video explaining what that is later. So I'm going to give you an example of how we can use signal detection theory to try to understand some problems that we might come across in the modern day. Let's start with police lineups. So what is the best way to identify our perpetrator? Oftentimes people will just go with accuracy. But that might not be the best way of doing this because we're concerned about false alarms, right? Because false alarms could be very, very serious in this context. A false alarm is a false accusal or a false conviction, and that has a huge amount of bearing on someone's life. So we need to think about it using signal detection theory. And we can test this using two different kinds of tests. A simultaneous lineup, which is what you traditionally see, where you have 6 or 7 people lined up and you have to try to guess which was the one that you saw, and a sequential lineup, which was kind of a new method that people were using to try to do this better. And they're going to show you individuals' faces one at a time, and it's your job to correctly identify who it was that you saw. So let's try this out. Which was the man that you saw at the start of the video? If you remember, on one of the very first scenes, we had a face that skidded by. Try to see if you can remember who that was. So let's start with the sequential lineup. Okay, so did you notice him? Did you find the one that you were looking for out of those 6 people? Let me give you a simultaneous lineup for comparison. Okay, so which of these two methods were easier? And in case you forgot, the face that you were looking for was this one right here. So it would have been the 5th one presented in the sequential method, the one in the top right here for the simultaneous method. So let's look at some hypothetical results now. Let's say that the sequential method had 80% accuracy, but the simultaneous method had 60% accuracy. If those are the results that we have, it seems like the sequential method is best. It seems like because that's going to help us identify the criminal more of the time, then that's good, right? But we need to break it down to look at signal detection. And if we do that, we can see that the sequential method has an 80% hit rate and a 60% false alarm rate. That's a really high level of false alarms, whereas the simultaneous or traditional method has only a 60% hit rate, but a 10% false alarm rate, much lower. So it seems like the sequential method is going to be best to help you find the perpetrator, but the drawback is that there's going to be lots of false convictions that come along with this. Now, whether or not that's a sacrifice you're willing to make depends really on the kind of morals or the values that you place on the criminal justice system here. So, using signal detection theory, we're able to get a better look at the data, a more sensitive look at the data. So, that's it. That's a crash course on signal detection theory. It gets you through the basics. It doesn't cover some of the more advanced things about signal detection theory, like criterion shifts or how to calculate D prime, but it should get you enough through to understand what people are talking about when they're talking about using signal versus noise or signal detection theory as a way of analyzing new data sets. Thank you so much for listening.